I think we should start. It's 3 o'clock. So, thank you for coming here. My name is Ragavan, and I'm going to talk about how to implement Selenium Grid on Kubernetes with Docker traffic and help. So, how many of you know what Selenium is? Selenium automation, great. And how many of you know Kubernetes? Great. Yeah, come in. You can come in. Yeah. So normally, when before I start the talk, I would like to convey like what you're going to get out of this. I learned Kubernetes by myself when I thought like the Selenium Grid concept I had wasn't scaling up, right? So what you're going to get out of this is, in case if you know Selenium Grid and you can use Kubernetes, there are known knowns and known unknowns that you don't know, and sometimes you can use Selenium Grid on Kubernetes, but you don't know how to do it. So either way, you will learn what my experience, my journey is, and then I'm going to share that for the next 45 minutes to 1 hour. So before we go into the solution, what is the problem that this solution is trying to address? So I'm going to go through like 5 problems that this is trying to address. Because there's no point in just go and implement it because Kubernetes is cool or it's nice to use a different technology, but what is the use case and what is the return on investment on the business for your company, what you're bringing back? So the problem 1 is key tenets of continuous testing pipeline. If you take any software company in the world, everyone, all they are trying to do is take a code change, move it to production with quality and faster. That's what everyone is trying to do, whether it's Amazon, whether you sell apples, or whether you sell anything, as long as it's a website or any web portal, that's what's happening. Anything that's around it, any observability tools and anything is trying to catch if something you're not doing correctly in your pipeline, what if it goes wrong? So you're monitoring your production and other things. But if you do things right and follow all the key tenets in the CI/CD pipeline, you're good, right? So what are the tenets and how it is related to my presentation? Failing often is one of the principles, which means run your test frequently. By the way, Selenium is for UI automation, to run your test on browsers, right? So failing often means run your test frequently. If I run my test frequently, I'm going to get faster feedback cycle. As you are changing your code, right? If you can test more frequently, then you're going to get more faster feedback, so you can take corrective action. Instead of, in many companies, I hear that people run automation overnight because it takes few hours. People run automation over a weekend because it takes so many hours. The problem that's going to happen is when you do that, your developers are going to give you a big chunk of change, and you're going to test a big chunk of change. And when something fails, now you're going to talk to 15 different developers, like, okay, which change caused the failure? But if you can test as and when your own change, when something fails, you know that is your change is causing the failure. So fail often means run your test frequently. To run your test frequently, you should be able to run your test faster. If your test, if you have 100 UI automated tests, and if it takes an hour to run, you cannot run tests frequently. That's running slow, right? So the other principle is fail fast. It's same as fail often, but fail fast is whatever you run your critical test first, so that again, when something fails, you get much faster feedback cycle. Again, for this, you should be able to run tests faster. And whether you fail often or fail fast, do it close to the code, and that's shift left. So instead of doing things to the right side of the pipeline, after you merge your pull request or committed your change, do it close to the code. Do it close to the code in the sense, in your branch itself. If you're using GitHub, right? Do it on your branch. Deploy it somewhere, run your test, so that only change you have there is yours. If something fails, you know you might have caused it, you can fix it and go on. And when you merge your pull request, in that case, if you follow shift left, your pull request is already production ready. It can go to production, right? So for all these three things, fail often, shift left, fail fast, one of the key component is to have the ability to run your test in a concurrent fashion. Because the faster feedback cycle is important for this concept to work fine and for developers to be productive. And which test fast means if you have 100 tests, if you run them in sequence, it's going to take 2 hours. Would you be okay waiting for 2 hours to know the feedback cycle? No, nobody would be interested. So test fast is how you can parallelize your test, so you can run all 100 at the same time and finish it within 10 minutes, and you get faster feedback. And that's the key component of the presentation, how you can implement Selenium Grid in Kubernetes, so you can help this test fast concept, not just for you, for your team, for your entire organization. So you can scale at will across your organization. The second problem is people, I see lots of companies, they try to run Selenium Grid in a data center or in Jenkins, where if you run automation in Jenkins, your browsers are going to be opening in executors, and that's not going to scale well, right? You only have one executor. You can probably maximum open 5 browsers there. And the another problem is if your job is aborted, then those browsers are going to be stuck there, and your executor is going to become unstable. And data center, people think that it's there, it's free, but data center is not free. I have a deck to show how much it costs per box level in a data center because of cost of electricity, air conditioning, employing people to take care of data center. The third problem is micro-frontends. So somebody, I think Albert Einstein was giving some question papers to students in Oxford University, and one of the students asked, like, Mr. Einstein, you gave the same question paper last year. Why are you giving the same this year as well? So for that, he replied, the questions are same, but the answers have changed, right? 10 years ago, it's very normal to release once in 6 months. I've seen that, right? But right now, people release even every pull request go to production. So how can you make that happen for anything that runs on the web browsers so that you can run them faster and faster feedback cycle? And so basically, micro frontends, you take monolith and change that into like 10, 15 different micro frontends, and they all run on their own pipeline. And they all have their own test cases to validate, and they all go to production on their own. So how can you help microservices go to production with quality? So that's, again, a speedier, a scalable Selenium Grid on Kubernetes is going to help you. And this is a visualization of what I just said you're seeing, where you have a master main branch, and different engineers in the project is branching off and working on different pull requests. And with shift left, what is happening is every commit or every branch can be deployed, deployed, tested for using UI automation, using Selenium Grid, and both the stack of the application and the Selenium Grid can be destroyed. But this concept will not work if you only have one Selenium Grid in your data center running, because it's just running one version of browser. But one of the branch of your project, one of the developer might need to run it on Firefox. Another developer might need to run on Chrome. Another one need to run on Chrome version 101. So this, what you see here as one grid, one Selenium Grid with, say, 100 browsers, is not going to scale up for the new use cases. So what is the solution? Is to have every branch, every deployment at branch level should be able to create a grid on demand. Okay, I need 100 browsers, give me in 30 seconds. I need 50 edge browsers, give me in 30 seconds, right? So that level of scalability, not just for one pipeline, for your entire organization, how good that be, right? How much productivity it'll bring. And that's what we are seeing, how if you can implement Selenium Grid in Kubernetes, that's the problem it's going to solve you. So here we are talking about shift left, but even if you are not following shift left, if you have bunch of jobs running UI automation for different projects, each job can say, demand, okay, give me 100 browsers, and they can run it and destroy it and give the resource back to whatever cloud provider you're using. So this is another problem we are trying to address. The fourth problem is multiple cloud accounts. Like when you start migrating cloud, you will have one account or two accounts, one test and one prod, right? But when you grow into cloud and you adopt more and more stuff, it's natural that you're going to have many, many cloud accounts. One part of your organization is deploying apps in one, and another one, but your Jenkins and CI/CD infrastructure will be shared. So you should have a solution where when you run your Selenium Grid, it should be accessible from anywhere in your organization for any apps, right? They should be able to make use of this and run it. So that's another problem we are trying to solve. The fifth is the most important one. The important one is the cost, because nobody's going to invest when you say it's going to cost you $300,000, right? Nobody's going to invest. Nobody's going to be interested, even listen to you at CTO level, because normally automation and QE is considered as a cost center, not a revenue generating thing, right? So SaaS platform where you have lots of browsers and other things, but they charge you based on number of parallel browsers you can hit. So imagine you have a big organization and you want the whole organization, every team to go faster, and you want to get more and more connection. You're going to be paying like at least $500,000, because that's how they charge. That's the business model is. It's not going to scale. So the cost is going to decide how fast you can go to production, how quality your application can be. So that's something this is trying to solve. If you run your browsers on EC2 instances, then the amount of fine-tuning you can do is limited, because you will overly allocate. Instead, if you are on a container, you can allocate memory and CPU at millisecond level, at megabytes level to your browser. And you will see what I'm talking about. And data center is costly as well. There's another separate deck. I'll show you why data center is free. Normally, when we think data center, oh, it's there. It's our data center. I can run whatever I need. But it is taking money every second of the day. So the problem 1 to 5 is what we are trying to solve. But when we came up with the solution, the 6 is we decided, okay, it's going to be Kubernetes. We are going to run browsers inside Kubernetes. But then you should point your automation to the grid, and your automation should go and hit inside the browser. It's running inside the Kubernetes cluster. So you need a way for those traffic to get inside the Kubernetes cluster. And that's the external traffic problem. So the solution, what we implemented is Kubernetes is a container orchestration platform for management of container application. We decided like Kubernetes is a perfect choice for this. Docker performs operating system level virtualization, known as, you all know Docker. So it's Kubernetes, it's going to orchestrate Docker containers. And we use Helm chart, which is a blueprint for Selenium Grid or any application. We use Helm chart for that. And traffic is the reverse proxy. That's what is helping your automation traffic to get into Kubernetes and hit the browsers, right? So traffic is a reverse proxy. We will take a look at that in deep. So here, what you see is the overall big picture of the Kubernetes cluster, right? If you implement Selenium Grid on Kubernetes cluster, this is exactly how it will look like. You know, most of you said you know how Kubernetes looks like. So you have a control plane which sits within the cloud provider, and they manage it. And then on the other hand, you have worker node. Worker node are basically EC2 boxes. These are worker node, as you see here. This is just an example of this here. And I have 2 worker node here, right? And worker node are basically EC2 boxes, or in terms of AWS, but it could be plain VM boxes in different cloud providers. So what you have in the control plane, it runs within the AWS side, and then you have worker node, and then you have pod. So a few terms in Kubernetes is a pod is basically can encapsulate one or more than one container. It can run more than one or more than one container. In Kubernetes, a concept of service, a service can handle a group of containers in terms of communication. And kubelet, for every worker node, here you see two worker nodes. This is one and this is two. Each worker node has default processes running. One is kubelet and one is proxy. Kubelet takes care of making sure containers are running within pod, and proxy makes sure that your rules, network rules, are respected, and it takes care of that. So if you have 50 worker node, which means 50 EC2 instances, everything is going to have a kubelet and a proxy. Now, how this is going to run your browser is within each worker node, if there is one pod, it has two containers. Each container can have, say, Firefox, Chrome, or Edge. And same thing on the other side. So this is how a normal cluster looks like when implementing Selenium Grid, and this is how it's going to run. Here, for a pictorial purpose, I have put two containers within a pod, but implementation-wise, it's going to just have one browser in pod for reliability purposes, right? So this is the overall look and feel of the cluster. Now, if you look at, before going into more detail, I would like to just quickly explain, because this is an outlier in terms of anything. What is traffic? Why we need that, right? So as in the previous image, you saw that we should be able to point our automation to a URL, and when you run your automation, it should be able to go and hit these browsers like they are running locally, right? How can you make it make sure that your automation framework can actually, when you run, can go and hit the browsers running inside the cluster? So there are different ways to getting in external traffic to your Kubernetes cluster. You can use cluster IP, you can use node port, you can use load balancer. But one thing what we are using is ingress, because now you can have rules. Why we need to have rules? So for that, we can use traffic or Istio. But you may ask, like, why do we need that? Why can't we use load balancer? Because when you implement a solution, you don't just implement it for you or your team. You make sure that your implementation is very generic and it can scale to your entire organization. It can scale to the rest of the world. So you implement it in such a way that anybody can use it. Anybody can use it in a scalable way. So why we need this is, at any point in time, the way it is implemented, if you have 10 different teams, they can create 10 different Selenium Grid and run it. But they're all pointing to one cluster. So how do you know when one automation framework is hitting one particular Selenium Grid, which browser to go and hit? And that's what traffic is solving. So traffic is basically a ingress, a rule-based engine where it says, where, for example, if you hit foo.mydomain.com, the rule will say, okay, if that's the case, then you're going to go and hit the service called X. If I hit mydomain.com/bar, then the rule knows which service inside the Kubernetes to go and hit. So that's the thing that traffic is taking care of. Now, looking further and mapping that to Selenium Grid, so I have 3 Selenium Grids running at the same time here, right? I have Hub Demo 2, Hub Demo 1, Hub Demo 3, okay? And they're all running behind the same load balancer. So when I point my automation framework to Hub Demo 3, the rule engine here, what you see here, is going to tell the cluster, hey, if somebody hits Hub Demo 3, hub.test.company.com, send those traffic to Hub Demo 3 Selenium Hub service inside the cluster. So they're all properly isolated. It knows where to go and hit, which browser to go and hit. And as soon as it hit the service, and service knows it can only transfer it to the hub, because I say the port is 4444, and then hub takes care of it. Hub does its normal job of load balancing. And you can have 50 grids like this. across the organization, scaling with no problem of running automation. And there's no more problem of automation taking hours to run. There's no problem of, let's ignore the automation and go to production, and you incur severe loss. Right now, because of this, you don't have any scalability problem at all. You can scale as much as you want. You can, each of these grids can even run 100 browsers at the same time. Right? So imagine if you can run 100 tests on 100 browsers at the same time, it's going to be finished within the slowest test case. Right? If your slowest test case takes 5 minutes, you're going to finish running all your tests within 5 minutes. So this is the idea. So, and you can also see here one grid somebody created, hey, I want to run on Firefox, and somebody created another one, I want to run on Chrome. Somebody created Edge, I want to run on Edge. Now, there are other things what I learned I'm sharing here as well. So when you implement, you also have to make sure that its security-wise is foolproof. So you can restrict who can access the grid based on your source IP address. You can actually give your CI/CD infrastructure. You can give your VPN CIDR numbers and other things, so that it's not exposed to anything that is not necessary outside. Right? So this is something you can take care in your Helm chart itself. Who is going to access this so that it's more secure? Now, in terms of autoscaling, if we have 10 grids and people are creating like 100 browsers each, what is the best way to scale? What is the best way to scale? And there are two different types of scaling, and there are two levels of scaling. There is horizontal scaling. Horizontal scaling means you have a small app, but you increase the number of stuff to scale. Vertical scaling means you increase the number of CPU and memory to increase the size of the VM or something. Like, for example, you have worker node. When I create 500 browsers, I need enough worker node, right? So instead of choosing a medium-sized box and creating more, that is horizontal. Instead of choosing a very large box like C5 9x large or something, C9x, C5 9x large, that'll be a bigger box. So in terms of reliability and best practices, I would always go for horizontal scaling. So what you see here is at worker node level, you choose a medium-sized box like C5 2x large and scale it so that you can have more number of pods on it. And at the pod level, you increase the number of replicas of the pods. I want 100 browsers, I can just create more replicas. Instead, if it is vertically, you will have one pod and run 10 browsers inside. That's not reliable. There's more resource sharing. You have to, all 10, 15 browsers are going to share the same resource. So that's not best practice. So always go for horizontal scaling. That's the best and more reliable as well. Now, how I envisioned this to be used by any team across the organization is you create on demand, you scale, you run your test, and you terminate. And this could go on across the organization, regardless of how many teams you have. You might have 50 teams. Everyone can do this on their own pipeline. So there is no scalability problem at all. So you create the grid, then you scale the browsers to however you want, and you run your tests concurrently. So that's something you have to make sure that your framework can do. If you have 100 tests, you should instrument your Selenium Java TestNG or Nitro.js or WebDriver.io or any Selenium-based or Playwright can also run on Selenium Grid. Make sure you enable the framework to run them concurrently, which means you're actually making use of the parallelism. And then once you are done, just destroy the grid and give the resource back. So that's exactly what the cloud is for, right? You use when you want it, and you pay for what you use. Now, I want to pictorially show what's actually happening when you scale in the cluster. So when I create, so this is a Helm install command. I'm saying, I want to create Chrome. That's what the Chrome enable true. I'm giving the directory where the Helm chart is. I'm giving a namespace. What is the name of my grid? And then a config file to access my cluster. So it's going to create a grid, a plain grid with just hub and one node. And it's going to give you, I can access this via this URL. So this is the beauty of having the traffic and load balancer so that it's accessible anywhere within your organization. And you can point to your automation and say, hey, this is my grid, run this. And this is dynamically created as well. Now, once you create the grid, you now scale it. Like, okay, I have the grid. Now I'm going to replicate the browsers to 50 from 1 to 50. So now you have 50 browsers. That's Chrome replica count, and you say upgrade, and now you're going to have 50 browsers. Now, once you run your test, and all of them finish within 5 minutes, now you say, I'm done. I can destroy it. Right? So it's all on demand, and you can scale as much as many you want. Now, this is how, if you use this across the organization, this is a snapshot to show how you could actually use it. Like, for every branch, you could give the grid a name of your branch and create it and destroy it, right? If you want to follow shift left and you want to run more and more tests, then you can create grid at different, for every branch and then use it. So, I just named the each grid with the Git hash just to give you that perception, like I can use it at a different branch level. Now, I'm going to pictorially show how, visually, how the autoscaling works at both worker node level and pod level. So when I say, by default, when you have a cluster, you will have at least minimum one worker node, right? Worker node is just easy to instance running. Nothing is happening. The key core components of clusters are running here. Now, when I say create a grid, a hub will be created, and a node will be created, which is running one browser. Everything is fine. The same EC2 box have enough space, enough CPU, and enough memory to actually run this. But now I'm saying increase the Chrome by 35 or 50 or whatever, right? Now, when I say this, the cluster doesn't have enough worker node to run those extra 35 pods, browser pods. Each requires around 1 GB of memory and probably half a CPU. What's going to happen is Kubernetes is going to scale your worker node first. The EC2 instance is going to scale up, and it's going to create, I need 35, and based on the Helm chart, each pod requires this much memory, this much CPU, estimated, I need to scale up by 5 more nodes. Once the worker node is scaled up and it's up, then it goes and create the pods, and now you have 35 browsers. And then you can run your test, whatever test you're running, concurrently, and once you finish, you call I'm done, uninstall, or destroy. Uninstall is a command. What's going to happen now is your pods will be destroyed, and the hub and node, everything will disappear. Resource is not yet given back to AWS because the EC2 instance are the resource, and they are still running. And now that because you have autoscaling already configured, and with minimum how many EC2 instance should be running, and based on your settings, it'll look at, no, nothing is running for the last 3 minutes. I'm going to scale down. So when you're not using your AWS resource have scaled down, you're not incurring any cost. So that's the beauty of cloud, where you are using only when you need it, and you're only paying for what you're using. You're not running on data center, or you're not using any expensive SaaS platforms. And so in case if you're using EKS on Fargate, then you don't even need to worry about underlying hardware, because AWS takes care of, like you say, I want to deploy 10 pods. AWS take care of underlying hardware, and then it takes care of deploying it. You don't have to worry about, oh, did I choose the right box? Did I choose the right CPU optimized box or right network optimized box? You don't have to worry about anything. AWS take care of it. And that's if you use AWS Fargate. Now, what is warm worker node pool, right? So basically, as I showed you in a couple of slides before, if 5 different teams are creating a grid with 100 browsers each, they're going to see some delay because there's not enough worker node available for them to give an instance browser. Probably they will see like 2-minute, 3-minute delay, right? Why they are not? They are saying it because in your autoscaling setup, you have always said it's enough to maintain 1 or 2 minimum worker node all the time. But that's 2 is not enough to create 500 browsers. So based on your usage, how big your organization is, how often you need grids, you can say, because we want a faster creation of grid, I want to set my minimum worker node pool to be always running to be X. It could be 4, it could be 5, it could be 6, depending on how fast you want. It's a trade-off of waiting for 2 minutes, that's all. You're not waiting for 10 minutes for EC2 instance to be created. But if you want instant grid creation, you might want to set your the minimum worker node instances to be 4, 5, whatever it is. Because they're going to keep running all the time, they also might incur some cost. Right? So that you should keep in mind because there is a cost involved. Then this is HTTPS based, which means you don't have to worry about security. You can enable a user authentication for every grid. You can have a username password set as well, and it's HTTPS based, which means all your traffic are encrypted and you don't have to worry about it. And for any framework, because it's HTTPS, you just need to change the settings to the port, for example, in Nitro.js, instead of 4444, you set it to 443. And there are some settings that you need to follow for your test framework to work properly. So this is a key thing, resource quality of service in Kubernetes. Very, very key, important thing, which I learned as a trial and error method. Quality of service. What is quality of service in Kubernetes? There are 3 types of quality of service: guaranteed, burstable, and best effort. What happens in Kubernetes is when so many pods are running, right? When new requests come in to create new pods, the Kubernetes will look at, okay, who I can kick out so that I can accommodate the new guy. And the kick out thing, how Kubernetes decide who to kick out so that I can accommodate the new pod, is based on the quality of service. The first type of pods to get kicked out are if they are classified as best effort. The second are burstable. The last one to be kicked out are guaranteed. So how can you make sure your pods are guaranteed? Because you don't want, when you're running automation, you don't want your pods to be kicked out and your automation fails or become unreliable. So basically, if you want your pods to be guaranteed quality of service, when you add your request for memory and CPU in your Helm chart for your browsers, you set your request. Request is how much memory and CPU you need, and limit is how much in memory maximum you can go for. And those two should be exactly same. If you set it, then Kubernetes will interpret it as, okay, this guy, I'm looking at request and limit as exactly same. I'm going to mark this quality of service for these pods as guaranteed, which adds reliability to your grid, where your grid is going to be more stable, because anytime somebody comes in, new request comes into the cluster, these pods are going to be the least or the last to be kicked out when there's a resource starvation. So this is an important thing to understand. But it's not always the case for different applications. For Selenium Grid, it's true, but for different applications, you may not want to set the limit because it may be resource intensive and other things. So this is just for Selenium Grid. Another experiment I did is, should I run more than one browser in each pod or just one browser in pod? And it's most reliable if you and cost effective if you can just run one browser in one pod, right? So if you have 50 browsers, you have 50 pods running different browsers. And in Kubernetes, by default, when you create, you need to give at least 2 subnets, so that your grid, your hub will be in one subnet, your nodes will be in one subnet. Before I implemented this solution, I had another solution which is pure EC2 based. I used to see forwarding to node failed errors, but in Kubernetes I never saw that, because probably it's all managed within the control plane, and within Kubernetes it manages very well than a normal EC2. So it's no longer an issue, and it works really well. So this is another one which shows you how changes in software is also changing or increasing the cost. For example, many years ago, when I had an EC2-based solution for Selenium Grid, there was no Gecko driver for Firefox. I was able to run 24 Firefox instances on C5X Large. But then they introduced a Gecko driver. So because now every browser is going to have another process attached to it, it needs more CPU, it needs more memory, which means after that, I was able to run only 15 browsers here. But now I moved to Kubernetes, I can only run 8, because every worker node, as you saw in the previous decks, like way before, each worker node is going to have its own processes running default. So you need to allocate some CPU and memory to it as well. So, but still, it's much cheaper than running on EC2, mainly because you can allocate CPU and memory at megabyte level, at millisecond. I can say, I want this browser to have only 400 milliseconds of CPU time. That level of granularity I can allocate to browsers. So imagine that means that you're controlling your resources to the lowest level of unit of CPU cycle time or memory. So you're using the resource in such a brilliant way. Using Kubernetes is very cost effective. This is another important thing. If you are running your cluster, Kubernetes, if you're running your Selenium Grid in your existing cluster, where other applications are also running, the thing is, whenever Kubernetes create worker node, right, it allocates X amount of private IP address to that per interface. Now, what's going to happen is, in Selenium Grid, you're running at scale. You're running more and more browsers. What's going to happen is, for example, if my worker node instances are C5 2x large, and if I scale so many browsers, and suddenly I have 10 different C5 2x large, Kubernetes will allocate 30 plus private IP address to each of these boxes, right? Now, I know for a fact I can, based on my memory allocation and my CPU, I can only run 10 pods in that box. But Kubernetes has allocated 30 IP addresses, when I know that I only need 10 IP addresses. But Kubernetes is saying, no, I give you 20 more. What's going to happen is, when you scale, you're going to unnecessarily allocate more and more private IP addresses. At one point, other application will not be able to deploy because you don't have enough IP address, right? That will be like a big red alarm going across the organization. Like, you don't have IP address in your subnet, in your VPC. So the solution is, there's something called AWS VPC CNI, where you can restrict based on your configuration, your memory, your CPU allocation to browsers, and say, hey, I know in this type of box, I can only run 10 of my application. I'm going to restrict how much private IP to be assigned to this box, and I'm going to set it to 10. This way, you are controlling how many private IP addresses are allocated to each instances. This is a comparison of cloud providers versus Selenium Grid. Imagine you want to have 100 parallel connection, right? It will cost you around $240,000 per year upfront for the rest of the year if you go for enterprise license. And it means whether you use it or not, that money is gone. You already paid that money. You're not going to get back. If you use Kubernetes and this solution, there is no limit of 100. It's not 100. You can even run 1,000 cases across your organization. And it costs you like $50,000. The license type is fixed, and here is pay for use, right? It's mainly because we are using spot instances. We are only using when we need it. We destroy and give the resource back. So it's more cost effective. And this is what I was referring to in the previous slide in the beginning. Data center is costly. It's because if you calculate a data center and say how much money you're paying for rent, for air conditioning, for electricity, for employing people, to building rent and everything, and if you calculate and divide and allocate that cost to each machine running in the data center, one large box will cost $10,000 per year. One medium box will cost $8,000 per year. One VM will cost $2,000, right? And this is why we have to change our mindset and see like, oh, data center is not free. It's there, yes, but it is costing money every day. It is much cheaper to run on cloud, and that's why companies are moving to cloud. So this, you can understand like why Selenium Grid on Kubernetes is much cheaper, right? And this is another way of saying, like across your organization, if you have n number of teams, and n could be 50, and you are running n different pipelines. Now, if you want your organization to have, if you want your application team to run much faster, go to production faster, be productive, and if you go to a SaaS company and say, can I have 1,000 parallel connection? You're going to paying millions of dollars, right? And that's what it's solving right now with Selenium Grid. There's no such thing. There's no such scalability issues. Your cost is minuscule. Spot instance. How many of you know what spot instance is? Great. So, spot instance is basically somebody already paid for that in AWS, and AWS say, hey, these guys are not using it. I can just loan it for you for a very cheaper price, but on one condition, I'll pull back with just 2 minutes of notice. It's much cheaper to use spot instance for your automation, because your automation, if you write it properly, short automation, run 2-3 minutes, you're never going to see any problem of that termination. Plus, if you use managed nodes in Kubernetes, Kubernetes automatically in the back end look at, hey, this machine is going to be pulled away it can predict if you use managed node. It can predict saying, these nodes are going to be gone away. I'm going to replace it even before the request comes in. So it's more of a proactive approach. So there's no reason why not to use spot instance. It's probably like 50-60% cheaper than using on demand. Unless your organization is bigger and you already have reserved instances, which is also cheaper, sometimes cheaper than spot instance, then you can use reserved instances. But otherwise, you can use spot instance. It's much, much, much cheaper. And this is the last 2 slides. I just want to say that just having a scalable browser infrastructure is not going to solve all your problem. You need to have your application have the ability to accept the throughput your test automation is creating. Because otherwise, there's no point. Your test automation is going to be flaky. It's going to fail often, right? So you need to scale your application so that it can take 100 hits at the same time. Not only that, when you run your test, where you run, whether it's Jenkins, whether it's Bamboo, whether it's GitHub Action, you're going to run 100 parallel threads at the same time. Can that box handle 100 parallel connections? So that has to scale as well. Otherwise, you're going to have 100 browsers, but you're going to be able to only run 10 test cases at a time. Waste of resource, right? So the scalability, it should be there at the Selenium Grid level. Your application should scale. Your application runners, your test runner should be able to scale to have a proper end-to-end, fast execution. So return on investment, like we're not just creating because it's cool, it's Kubernetes nice, I know how to do it. It's not. End of the day, when you create a tool, when you create a solution, what you're giving back to your organization, what is the value add you are creating to your entire team? What is the value add you are creating to your brand, right? Faster feedback cycle. Your developers they don't need to wait for hours to get feedback. Immediate feedback, which means they don't have to context switch on different story and waste time, right? So they can immediately get to the job and fix things. That's developer productivity. Developers will love it because now they don't have to wait for hours. They don't have to wait for weeks to know if their change has caused any problem. It saves time. And frequent release to production. Now you don't have to wait for weekly or bi-weekly release. You can just go to production with every pull request, because every pull request, even before it merged, can be validated, right? And for business, it helps you make money. Why? Because now you are releasing features faster than your competitors. Because competitors, business is about competition, right? Like if I'm releasing a feature and if I can get to customers 1 week faster than my competitor, that's a win for me, because my customers already adopted and they liked it and they're going to stick with me. And save money, because it's this type of grid helps shift left, and you're going to see less and less of production incidents. Less production incidents, more happy customers, and less problem to them. And that's exactly. End of the day is happy customers. That's the end goal, right? It's not running fast automation, but your moonshot vision is, as a key quality engineering, how can I make happy customers? And this is all about making happy customers, right? So that's the end of the presentation. And this is my LinkedIn and Medium blog. I'm happy to take any questions if you have. Thank you, guys.
One question. The hub URL that you were showing, what do you reach by going there? Is it sort of the test result of that specific hub?
So that hub URL is the way to reach the hub, send your test cases to the hub, and the hub will distribute the test cases to the worker node where the browsers are running. So in your framework, if you have Selenium, Java, or WebDriver IO, or Nitro.js, that's the endpoint. You tell the framework, hey, this is where I want you to run the test. And that's all you need to do. And enable parallelism on your test framework. When you run all of them are going to go and hit the hub. Hub will take care of distributing and running on different browsers in a distributed way. Cool. Thank you very much. Thank you.